Alright, let's continue. Dropbox, DIFC, that paper. Come on, give me a break. Workbook and slides, physics, mechanics. Rightio. Okay, if you can write this one down. Okay. Continue. Yeah. Got that? Yeah. Okay, so let's have a look. Right. Another way to state Newton's second law is like this, where delta P is the change in momentum. So before we even can continue with this, we actually have to first say what momentum is. So this is our first definition. So before we can understand this new formula, now, okay, new formula, it actually turns out it really is the same formula. But before we can discuss that, we have to talk about this new thing called momentum. Does anyone actually know what momentum is? You think you know? What do you think it is? Yeah. Now, what I mean by momentum is like the formula for momentum. Do you think you know?
I can imagine a diagram.
Yeah, no, that's what she's saying. No, that's what she's saying as well about the pendulum. What Matt is saying. But what the momentum actually has a definition. Like it.
Forward force and something?
No, not that one. Not that one. No. Ken, do you think we should? Anybody? No?
No, I'm trying to remember back.
Yeah. All right. Momentum is the product of mass and velocity. That is m times v. That's what momentum is. This is a new word. Have you seen this formula before? Yeah. And what are the units for momentum? So, yeah, it's got to be kilogram meters per second. Okay, have we got that? Continue. Yeah. So I want to prove that this formula is actually the same thing. So Newton said F equals ma. Fine. So that means F equals m times a. Fine. And we know that a is v minus u over t. Now if we start at the beginning, t is actually just t minus 0. So in other words, we can get F equals, on the top, mv minus mu, and on the bottom that's just the time, delta t. Okay. But what did I say mv was? It's momentum. But what's the difference between mv and mu? Well, it's the difference between momentum at the end and momentum at the start, because it's u and v. So on the top, it's momentum at the end minus momentum at the start over delta t. So actually you could think of that, well, that's just the change in momentum. The delta means change. So in other words, this and this is actually the same formula. It's just in this version you use acceleration, whereas in this version you use momentum. But they give you the same force. Continue? Yeah? I think a lot of people have seen this before, but has anyone seen this before? No? You think you have, yeah? Okay, continue. Yeah. So why bother using this new formula if the old formula works? Well, the reason is this new formula is very convenient when the time is actually quite small. So just so you know, we actually use this formula usually when this is very, very small. That's usually when we see these formulas, just so you know. And this guy here, this guy is actually important in physics. So we give him a name. That's called the impulse. The impulse is the change in momentum. That is the delta P. So that's called the impulse.
Is that an I?
It's an I, capital I. Yeah. Yeah. So, you can kind of think of it like this. That force, you could also say, is equal to impulse divided by time. Just another way to think about it, if you like. Okay. So here, let's start with a simple enough example. A 1200 kilogram car crashes at a speed of 20 and is brought to rest. What's the impulse? So, here's your car. It's a car. 1200 kilograms. And it's coming along, and then it crashes into a wall, and of course it comes to rest. And it's going at 20 meters per second. So what is the impulse? So the impulse is the change in momentum, which is the momentum at the end minus the momentum at the start. Well, the m is the same, isn't it? So you could write it like this, which would be 1200, 0, minus 20. The v is 0, crashed into the wall. So that is minus 24000 kilogram meters per second. So that's the impulse then. Why do we care about impulse? Well, impulse is the thing that hurts. So when you crash into somebody, like you're walking, you hit into the wall or you fall to the ground, it's the impulse that hurts you. It's all your momentum being changed. is what is really the problem. Especially when it's being changed quickly. So when your momentum suddenly goes to zero quickly, that's what you feel when you come to rest. Is this okay? This one is. So let's have a look here. Here's another example. So you have a hammer and it hits a nail. And it hits the nail with a force of 50 newtons. And the nail moves down with 4 meters per second. How long was the force applied? So you got your nail, you hit it with the hammer, and the nail moves at 4 meters per second. Now it doesn't keep moving at 4 meters per second, because what eventually happens to the nail? It stops when it gets into the wood. But let's have a look at this one. So if I draw the picture here for you, there's the nail. So what happens is there's a force of 50 newtons, but for a small time, obviously. Think like a few milliseconds. And then this was at rest, but then it starts to move at 4 meters per second. Yeah? Okay, so what's the time? So if I use this formula, delta P over delta T, I know the F, it's 50. 50 down, so minus 50. Do I know the T? I don't. Do I know the P? I could. Because it starts at rest, the MU is 0. What's the M actually? 100 grams. That's a pretty heavy nail. 0.1. What's the B? Minus 4. And the U is 0. And the delta T is what we want. So the time will be 0.4 over 50, which is 0.8 over 100, which is 8 milliseconds, I think. Here. So the hammer touches the nail for only 8 milliseconds. I realized I gave you the name of this. This is called the impulse. And this one is obviously called the time. But actually a lot of people call it the contact time. Because it's the time that you're in contact with it to give it the force. So it's the contact time. Okay, let me know when you're ready. Okay, continue. Yeah. Okay. So let's see next one. Yeah, I think this is one you could do. So you're just kicking a football. So it's a lot like the example of the hammer. Okay. So tell me what the impulse is, and then tell me what the force is. Okay, so try this one. 250-gram football is at rest, and a football player kicks the ball, and the ball moves with 10 meters per second. A, impulse. B, force. So, what's the impulse? What's the impulse? Yeah, because it's 0.25 multiplied by 10, so the impulse is 2.5 kilogram meters per second. Okay. Now, what's the force? Let me think. Let's see if I can do that in my head. So the F is delta P, the impulse over the time. So 2.5 over 0.1. So 25 newtons. You got 25? No. What did you get?
0.25.
For the force or for the impulse?
Force.
Ah. How did you get that? What did you type in?
2.5 over 100.
Ah. It's 100 milliseconds. So that's 0.1.
Okay.
Yeah. Okay, continue. Continue. The biggest advantage to using this formula is that it allows you to calculate the force provided by rockets. So if you think about the hot gas coming out of a rocket, it has a mass and a velocity. But the gas was at rest, so there's a change in momentum. So by Newton's third law, this will actually cause the rocket to move. So actually, let me just draw this for you so you can have a good picture here of what's going on. So here is my rocket. And it's full of gas, we'll say. Okay. And then what happens is, let me draw some of the gas in. Some of the gas fires out the bottom. So I'll just draw it like that, the gas coming out, okay? Let's just imagine we look at this happening over 1 second. Okay? What has happened here? The gas is at rest and now it's moving. So its momentum changed. So you have mv minus mu. Now, which one is zero, the mv or the mu? Mu. So the delta P is mv. Is v up or down in this picture? Down, so it's negative, okay? So you can say that the delta P is less than 0. But the delta T is 1. So if I divide both of these by delta T, divide by 1, I get delta P over delta T is 0, less than 0. But what's delta P over delta T? It's the F. Okay? So the gas, it has this downward force. But according to Newton's third law, every action there's a reaction, the rocket will feel an upward force. And this is what actually makes the rocket move up. So this force is called the thrust. And it's very simple to calculate. It's simply the mass of the gas per second multiplied by the gas's speed. Because this is like delta P equals mv. This is like the v and this is like the m. So in other words, I suppose, do I have it as a formula here? I did do that. Yeah, so actually you need to write this down. So just to make it a little bit clearer, it's the speed of gas times the mass, it's not writing, I know, mass of gas per second. Now let's see how good I did without looking. Oh, There we go. I didn't do too bad without looking. This is the formula to calculate what you might call the upthrust. Okay? You hanging in there?
Barely.
Okay. Continue? Yeah? Let's see. I think I've got probably have just one example left to do. So actually, it's quite a simple formula. You know, if you have your rocket and you know how quickly the gas is coming out, and you know how much gas is coming out, you just multiply those two numbers, you know what the force is going on. Not a difficult formula. But what's interesting about this formula is you can use it for wind problems. Because when you think about it, if there's a wind blowing against you, that's a lot like a gas coming out of a rocket. Except instead of the gas being very hot, it's very cold. Instead of the gas moving very fast, it's moving very slow. And instead of a lot of gas, it's a little air. But it's the same idea. So let's have a look at an example. Here's a real example. It is a windy day. A physics student was walking home. The student stops for a moment to calculate the force he is feeling from the wind. The wind was blowing at 12 meters per second into the student, who's stationary. The student is 1.6 meters tall and 40 centimeters wide. Assume the density of air is roughly 1 kilogram per meter cube. What is the force felt by the student? So let me just draw this picture here so you can see what's going on. So here's my student. So I picture the student is like a rectangle. That's how tall? 1.6 meters tall. How wide? 40 centimeters wide. Okay. And he has this air that's blowing into him. So I'll picture the air like this. This is the wind. And it's blowing into him. Okay. And we know that this is going 12 meters per second. And we also know that the density of the wind is 1 kilogram per meter cubed. And we know its speed. Okay. And believe it or not, that's enough information to work out what the force he feels from the wind pushing him. Now, let's begin. So, Newton said, or not Newton, well, it was Newton. We can calculate the force from the wind by using the formula we had earlier with the rocket. Okay? So the force from the wind, like as if it's like a rocket, because it's a gas just coming at you, it's the mass multiplied by the speed. Okay, do we know the speed of the wind?
Yeah.
We do. It's 12. Do we know the mass of the wind? We don't. But we do know its density. So what's the formula for density? Mass over volume. Okay, so what's mass? It's density by volume. Okay. So we know that the force will be 12 times the density times the volume. Okay, well what's the density here? 1. So 12 times 1 is obviously 12. Okay. Now, a little problem. What's the volume of the gas? How big is the gas? So in 1 second, because remember you always look at these problems per second. In 1 second, how much gas do we get? What's the volume? Who can work that out? Well, we know it's 0.4 multiplied 1.6. What's this distance?
1 centimeter.
More than
1
that.
meter.
More than that. 12, yeah. And why?
Because in each second.
That's it. In each second, it moves 12. So there was 12 meters of gas that hit his face. So it's going to be 12 times 0.4 times 1.6 times 12. Because these three make the volume, you know, x by y by z. Alright, so that's 144 times 0.4 times 1.6. I've run out of brain power. Okay, 144 times 0.4 times 1.6. Right, so that is 92.16 newtons. So that's how much force from the wind he feels. It's about 92.2 newtons. So if he doesn't want to fall, how much must he push forward? He must push forward 92 newtons as well. So you know when you feel the wind blowing at you and you have to push forward, what you're doing is you're cancelling this force, pushing you backwards. Otherwise you'd fall. So 92 newtons is it's pretty big. It's like the weight of 9 kilograms. So, just so you know, well, let's give you a second here. Okay, continue? No. So just so you know, what makes this different to the rocket? Not much. The only difference is, if this was a rocket question, there should be a big rocket here because the gas is coming out at the back. But instead of having a big rocket there, you have a person, you know. So just so you can kind of really picture this, the difference is like this. You have a rocket and you have gas that comes out and it causes the rocket to move to the left. Okay? Whereas in the example with the wind, it's more like this actually. You have a cup and you have a gas that's going into the cup and it pushes the cup to the right. But it's the same thing. The gas is making the rocket move left and the gas is making the cup move right. Because of it hits the bottom of the cup, which is where like the man is. But it really is the same idea. They're really equal problems. That's why we can use the same formula. Yeah. Okay. I think that's it. So we've got loads of time. My goodness, we were very smart today. No problems. So what you could do, you could use this time. I'll leave it up to you. If you want to start working on the projectiles, you know, because that's important, you can. If you want to work on this, you can. Oh, what about Newton's 3 laws? How does that one go? Or that one's not done? Did we get... No. So actually, you have 3 lessons to do for next week then. Okay, so you can get started now on those 3 lessons. Yeah, go ahead, Jack.